Engineering 305, example problem 3-5. Maybe that's 305. I don't know. Whatever. Kind of cool. The strain components at a point and a body under the state of strain are a strain in the x direction are equal to 1200 micro. The strain in the y direction is equal to minus 600 micro. And the shear, oh my goodness, my screen flipped out. And the strain in the shear strain in the XY is equal to plus 900 micro. Determine, so yeah, I wrote those down behind the box, but I still wrote them down. Determine the principal strains and the maximum shear strain at a point, at that point. Show those things on, show those deformations on a sketch. All right. How do we do that? Well, we're going to go through the strain transformation equation. So there's our strain transformation equations. Let's get rid of our problem statement because I wrote down the important stuff. How would you like to start? Would you like to start with the principal strains? Would you like to start with the angle? Would you like to start with the shear strain? The principal, the maximum shear strain. I'll tell you what I want to do. I want to start with the principal strains, P1 and P2, because that's just what I like. And so that's going to be the strain in the x direction plus the strain in the y direction divided by 2. And then that's plus or minus this big radical. I got to fill that in. Don't know why it skipped. And that's strain in the x minus the strain in the y divided by 2. And that whole quantity gets squared plus gamma xy, the shear strain, divided by 2 squared. Now you saw that equation 310 as I was copying it down, but I've got it copied down. And now what I want to point out is look at equation 311 because I'm going to rewrite 311 as gamma principal over 2 is equal to what's under the radical, the strain in the x direction minus the strain in the y direction divided by 2 squared plus gamma xy, the shear strain, over 2 squared. And since this is exactly that, I don't want to calculate things a couple times. I don't want to do that a couple times. So I'm going to wind up starting, even though I want to do the principal strains, I'm going to start with the shear strain because then I calculate that once and then I just plug that in. So gamma principal over 2 is equal to EX minus EY. So that's 1200 minus negative 600 over 2, that quantity squared, plus the shear strain over 2. So I can write that as, I will write it as 900 over 2 squared. And that's equal to 1200 minus 600 over 2. That's 1800 divided by 2. So that's 900 squared plus 450 squared equals, and then I'm going to do the math, and that's going to come out to 1005 micro. And I'm going to leave it like that because that's what this term is here. That's not my shear strain. That's not my principal shear. I really would have to say that gamma principal is equal to 2 times that, or 2010 micro. But now I've got that answer. This is good, but I'm still working with this here as gamma over 2 because I'm going to take, and I guess I could take this, lasso that, and then I want to copy and put that there and paste it. Oh no, that's not what I wanted. Oh my goodness. I want to trash can that. Oh man, I'm just gonna substitute in. I'm just gonna go. I'm gonna get my black pen back. The strain, the principal strain, P1 and P2 is equal to the strain in the x plus the strain in the y divided by 2. Strain in the x plus the strain in the y. So 1200 plus a minus 600 divided by 2 plus or minus 1005, because that's what's underneath the radical. And so that's equal to 1200 minus 600 divided by 2, 300 plus or minus 1005. So epsilon P1 is equal to, well, that's when I add it. So that's going to be 1305. And the strain in the other direction is going to be a minus 705. And so with my, oh man, they're not showing me my fancy pens. They're not showing me, I just have to highlight it. That one and that one. There's my answer. There's my principles. That's what I've got. Am I done? Show the principles on a plot, on a sketch. Doggone it. Otherwise, we were done. And honestly, I don't have enough information yet to do that because I need the angle. So slide all that out of the way, and I'm going to get my equations back up here. I got to get back to a black pen. Tangent of 2 theta is equal to gamma xy over strain in the x minus strain in the y. I would say I have to look those up, but if I simply do that, then I can, there they are right there. So that's equal to 900 over 1200 minus negative 600. So this is 1800. So that's equal to a half. So I'll go one step farther. 2 theta is equal to a tan arctangent of a half. All right. Now, if I draw that, my rise over my run is 1 over 2. So if that's 2, then here's 2, 1. That's about here. That's 2, that's 1, that's my angle. But that also shows up here. I can either have arctangent of half, or I could have arctangent of minus 1 over minus 2. So this is a valid angle, and that's a valid angle. That's 2 theta. So really, and we'll figure this out. I need to check the answer. But I believe that's like 29 degrees. Let me hold on. So it's not 30. It's about 26. 2 theta is about 26 degrees. But that's this one. There's also this one, which is 26 plus 180. And so 2 theta is also approximately equal to 206. So there's now 2 different angles here. Theta is equal to about 13 degrees, because I rounded off. I didn't actually round, I truncated, right? If you're looking in the book, following along, it's a 0.57, or I truncated. And then this other one is about 103 degrees. And if you look, those are separated by 90 degrees, right? So that's my X and Y face where my maximums are occurring. Now, I don't know which is which. Let's start making my picture. But I want to copy all this information over too. So I'm gonna slide this here, and I'm gonna say I've got my coordinate system. This is my x-axis. That's my y-axis. I'm gonna put the problem statement back up. Sorry, I had it up. And copy this information over here on the side. Strain in the x direction, strain in the y, shear strain xy, and it was 1200 minus 600 and 900. And then I've got my other pieces of information, which are now my principal strains, P1, P2, and my maximum shear. And that principal was 1305 minus 705, and my maximum was 2010, right? 2010. Now, let's plot this. On this axis, I have 1200. So I'm going to have, right, this is how I'm visualizing this in my head. I could go in, I could do a stress transformation and simply plop in those angles and figure this out. But I want us to be visualizing more circle. We already know it for stress. I know we're going to do another example problem. We'll do it for strain. But if I put that cube on here and I say, look, this is 1200 and this is, oh, sorry, it's going the other way. It's going the other way. That is minus 600. Now, in some ways, that's contradictory because I'm going minus and I show the arrow that way, but we understand. Can we do that? And then I've got shear, which is this way, 900. Now, I know one of the angles is 13 degrees. No, that's too high. That's too high. Going to look more like that. And the other angle is perpendicular. It looks like that. Now, one of those is 1300 micro, and one of those is negative 700 micro. Do you think this axis, you can't see that. You can't see that, sorry. Do you think this axis is the 1300 or the negative 700? It's too close to 1200. This is the 1305 axis, and this is the negative 705 axis. Oh, right there. All right. That's just using, I want to say, some common sense. You can see as I rotate up, I'm getting less and less of the shear, which is causing it, that shear is causing it to go up that way. I'm picking that up, and that's going from 1200 to 1300. At the same time, the negative goes the other way. So that's, sorry, I should get rid of that for you. That's how I know those angles without even calculating it. I could have gone back to the transformation equation that the strain in the n direction is equal to, and then I would have gone strain in the x direction, cosine squared, and dropped in the 13. And plus and we could have gone through that and calculated it. But I can see that. It's one thing to be able to do the math, but go beyond that to say, yeah, what is common sense telling me? What is my intuition telling me? And I'd like you to build that intuition up the whole time as well. So there's, in one way, our figure. If I were looking at the little block, this is in tension 1200. This is in compression 600. I've got a shear of 900, and then I'm going to have another shape which is 13 degrees off, and if I go this way, I'm at 1305, and if I come that way, I'm at negative 705. And that's principles. Then if I slice that on a 45, I can say, well, this way or that way is 2010. 2010. And all of this is micro as a unit. All of that is in micro. All right? There you go.